Here. Yeah. Okay, any other questions you thought of during the break? So I got one question on the boundary condition. You see, like in all these loops, we ignored I equal to 1 and we ignored I equal to 130, right? That means we are only changing U next in the interior of the domain, and the boundary is left as what? 0, right? That means we have 0 boundary condition. What would you suggest if we know the boundary condition is equal to something else? Just set it in the beginning, right? Exactly. Good. If we know the boundary condition is a certain value, is a Dirichlet boundary condition, we'll set it in the beginning. And every iteration, because we are doing U equal to U next, that is automatically copied. What if the boundary condition is a Newman boundary condition, which means the derivative normal to the domain is equal to something? Let's say is equal to 0. What would you do? Good. The suggestion is after the ij loop for updating the solution, if I know the normal derivative is equal to something, then I can update also the boundary values of U next according to the second value closest to the boundary, right? Because the normal derivative can be discretized into a difference between the second next value and the very first value at the boundary. And that formula can help you update the solution right at the boundary according to the solution one grid into the domain. Does it make sense? Yes? How do I define normals? How do I define normal at the corners? Very good question. You don't use it. Very good answer. So you never use the corners here, right? If you have so we are using a 5-point stencil, which means 1, 2, 3, 4, 5 point is like what I use. If you derive some other finite difference discretization, you may have a 9-point stencil or even bigger stencil that actually uses the corner value. And in that case, taking the average between the two adjacent values is can be a good approach. Yes. Yes. Very good question. So when do you convert the 2-dimensional array into a 1-dimensional array? Anytime you need to explicitly do a matrix vector multiplication or matrix vector operation, you need to put it in a 1-dimensional array. So anytime you need to do operation with a matrix explicitly stored in the computer, you need to flatten it into a 1-dimensional array. If you can convert all the matrix operations into stencil operations, then you don't need to do the flattening operation. It can be, I think it's more intuitive this way, right? I mean, it's a good exercise to go back and forth between the matrix form, like between the flattened form to this form. But I think it's a little bit clearer to me in this form. Any other questions? Ooh, I don't. No. Yes. Yes. If you do the flattening, you'll be using the immediate neighbors and also the plus n minus n points. Okay. I don't have a. Okay. All right. Don't know. Sometimes I have to do that. Uh, do you have a question like why the solution looks a little bit dark in the middle? The the boundary is zero, but like yeah, but I should get exactly the solution if I solve it exactly, right? I didn't solve it exactly, right? So if you look at uh let me see figure I am show you next minus u. Well, it's pretty small. It's dark, but like if I multiply by something 100 times, still dark, which may mean it's in the other direction. So let me do this. Oh, u exact, yes, u exact minus u. So let's do this first. So u exact is actually brighter than u in the middle. Yes, you have a question? Yeah, some points are much closer to the actual solution. The boundary points are much closer to the actual solution. The interior, it lights up, which means the solution is not as close to the actual solution. All right. And so first of all, I want to convince you that this is because we have not iterated for long enough. So let's make the iteration a little bit further. So let's do this again. It'll take a little bit more time, but let's see figure and I am show of u next again. I think we'll get something much closer to the actual solution. Right now, we no longer notice the interior to be much darker than the surrounding. All right. So it is because we haven't iterated for long enough. Yeah. It, okay, to answer your question, is the error big in the middle a general property of the Jacobi iteration or specific to this example? It is general for the Jacobi iteration that the error lights up according to the slowest eigenvector of the matrix. And this, what we are seeing here, is actually the dominant error corresponding to the eigenvector of the iteration matrix, which we are going to talk right now. Yes? If I what? If I split into a 2 by 2 and solve that independently? No. Uh-huh. Uh-huh. And still set the boundary condition only at the outermost edge? Oh, you're saying okay, does that depends on the actual content of the image or only depends on the shape of the domain, right? It depends on the shape of the domain. If I change the image to be something else, like an airplane or something, I should still get an error that looks like this blob. So you have very good questions. I gave you a lot of answers, but didn't tell you why. And right now I'm going to